Okay, so good afternoon, everyone. Today we have the pleasure to have Simon Pekar from SISSA, and he's going to talk about holographic derivation of BMS Flux-Balance laws. So the stage is yours.
Thanks, Erika, and thanks also to Gian Domenico who invited me to DIAS to give this presentation. I don't know if Gian is online and can hear me. So it's a great pleasure to be here to talk about this work that we did in collaboration with Adrien Ferrucci, Marius Petropoulos, and Mathieu Villat, who happened to be in the room. And well, also conveniently, the paper was appearing today, so it's very fresh work that I'm really happy to present here. Yeah, and it has to do with holography in flat space, derivation of BMS Flux-Balance. So if these words do not ring a bell to you, don't worry, because I will explain everything. And let's get started. So the main motivation, the broad picture of this work has to do with flat space holography. And what we want to do is to put flat space holography in a more solid ground than it is currently, trying to mimic as much as possible the steps of ADS CFT. And one of these steps is to identify what is called a holographic stress tensor. So in ADS CFT, this very well-known story, there is a holographic dictionary. But in flat space, there are many proposals for an holographic energy momentum tensor. And what I'm going to present is a way to sort of infer what is this energy momentum tensor from symmetry and from equations of motion. So I'm going to start with a reminder of ADS for gravity and classical holography. And then I'm going to move to asymptotically flat spacetimes and present to you what are the BMS flux-balance laws. And then I'm going to write down a proposal for a boundary variational principle from which you can derive these flux-balance laws. And this is an important step because although these flux-balance laws, they look a bit similar to conservation of a stress tensor, they are actually very different because they are non-conservation equations. Okay, so let's start with something that you may have heard about, and it's Graham gauge, which is something that we use in order to solve Einstein's equation in anti-de Sitter, so with negative cosmological constant lambda times 3 over L squared. L is the ADS radius. And what we do is we start by writing the line elements as follows. So there is an L squared in front. Z is sometimes called the holographic coordinates. It measures the distance between the conformal boundary of ADS to the interior. So this is SZ0. And the boundary coordinates, I will denote them here by x mu. Mu goes from 0 to 2. Okay, so what we assume is that h mu has an analytic expansion in powers of z, starting at z to the 0. If you are in dimensions other than 4, for instance, in odd space-time dimensions, that can have logs that appear in this expansion, but here we are in 4 dimensions, so this doesn't happen. And we go on. And there are 2 important quantities that appear. It's the piece at order z to the 0 and the piece at order z to the 3. This is because when you plug this metric into Einstein's equation with the negative cosmological constant, you realize that this piece is completely arbitrary, it's free. And this piece is free but subject to conservation equation. So if you plug this into Einstein's equation, what you get is that H0 is free, and H is traceless. And I compute the trace with respect to this metric and conserve. And again, the conservation is done with respect to the covariant derivative of this metric. So if you were to put, let's say, h mu nu is equal to eta mu nu, the Minkowski metric in 3 dimensions, and set all the rest to 0, this would just be the ADS metric in the Poincare touch. Here we are looking at non-empty ADS with potentially arbitrary boundary metric. If it is not equal to the Minkowski metric, we are talking about asymptotically locally ADS, or globally ADS if we take it to be eta mu nu. And this guy here has a name. When you start to do holography, it's the holographic stress tensor. Why? Because it has all the properties of the stress tensor for the conformal field theory, namely it is traceless and conserved. And all the other coefficients that appear in this expansion are then fixed in terms of these two quantities. So I'm just going to write it like this. Okay. So this is one thing. The other thing is that if we start from Einstein-Hilbert action with a negative cosmological constant, so lambda is over L squared, and we compute the variation of this action that we evaluate on this solution of Einstein's equation, this typically is not finite when you approach the boundary.
Sorry, just to clarify what you're saying here, you are not talking about the vacuum Einstein equations.
I am, yeah. I'm talking about a vacuum Einstein's equation. R mu nu is equal to R mu nu minus a half G mu nu R plus cosmological constant is equal to 0. The stress, maybe you're confused about the stress tensor.
Yes.
Okay, this.
So and what it means that something is completely free on the boundary.
Oh, it means that it's not constrained by Einstein's equation. Einstein's equation will take the form some prefactor times Hn, let's say, is equal to something else. But this prefactor develops some zeros for certain value of n, and these values is precisely 0 and 3 because they correspond to the scaling dimensions of certain CFT operators. So this is true that H0 is completely unconstrained. H3 is constrained, is also unconstrained, but it's subject to these two equations that I wrote here.
But is H0 not a boundary condition that affects the solution of Einstein's equations?
Sorry?
Is H0 not a boundary condition that will affect the solutions of Einstein's?
I will fix the boundary conditions later. For the moment, I'm just looking at the solution space of Einstein's equation without fixing any boundary conditions.
Oh, so that's why H mu is 3.
Yeah, that's why it's
affects boundary conditions.
Yeah, sure. I will fix it once I wrote this renormalized variational principle. Yeah, thanks for the clarification. So, okay, so this variation is typically not well defined, but there is a procedure called holographic normalization where you start with Einstein-Hilbert and you add boundary terms, which is typically the Gibbons-Fontaine-York term, and then some counter terms. I'm not going to explain in details how to do this because it's well known, and my focus is more on flat space. But when you do that, and you compute the variation, the on-shell variation of your normalized action, you will find something that is like minus determinant. Yeah, if I'm not writing big enough, please tell me. Minus determinant of the boundary metric, variation of this boundary metric, and now I'm really going to write it as T mu nu, where T mu nu is 3 over L and H mu nu 3. Okay, and from this, so this is finite at the boundary. This is an integral over phi. And from this form, you can see that if you take h mu to be fixed, for instance, to the Minkowski metric in 3D, then this is stationary. It's close to 0. And that's why when we're doing ADS-CFT, we fix h0 to be eta. It's no longer a free data. So this is a purely boundary action. It's stationary for directly boundary conditions. And the nice thing about this is that we can actually derive this part of Einstein's equation from it. How do you do that? Well, it's very simple. You realize that the conformal boundary of ADS enjoys the Weyl invariance. Right? It's a boundary at infinite distance. So there is an action of Weyl rescaling on the matrix at this location. The proper way to do it is to go to compactified space, conformally compactified spacetimes. But let's say for the sake of the argument, there is an extra symmetry that appears at this z equals 0, which is that I can send my boundary metric h mu nu.
Sorry, are you specifying the topology of the boundary?
Simply connected.
It's simply connected.
Yes.
You're telling us it's simply about, it's just a boundary.
I mean, okay, for all intents and purposes,
It's a two-dimensional surface, and it's simply connected. So
it's a three-dimensional surface.
it's a three-dimensional surface.
Yeah, for all intents and purposes, I would take it isomorphic to R3. Lorentzian. So yeah, we have this. I don't know if you can see it here, but we have this extra Weyl symmetry that appears that says that you can rescale. Sorry, this is a linearized Weyl transformation. You can rescale your boundary metric by an arbitrary function of the boundary coordinates. So, okay, how do you derive Einstein's equation from this variational principle? Well, you plug in this transformation, local Weyl transformation, and you require that it's a symmetry. So it vanishes for all values of B, and what you get is here the trace of T mu. Trace computed with this H naught. So here you get this, equation, and also you require that this action is diffeomorphism invariant, or a general diffeomorphism on the boundary. And from this is the usual argument, you get that this quantity here is conserved. Okay, any questions about this? So now what I want to do is to try to do something similar but in flat space, sending the cosmological constants. Now, if we try to repeat all the steps that I did here, you will end up with something very complicated and that we don't know really how to do in general, namely the holographic normalization procedure. But instead, what I'm going to do is to try to write something that looks like this in order to extract an energy momentum tensor and also some additional objects that I will define in a moment. And from this variational principle, to reproduce Einstein's equation, which is what we did here. So, yeah, the way of thinking about this is that I want to propose a boundary variational principle for asymptotically flat spacetimes, which reproduces Einstein's equations upon evaluating on local transformations like Weyl or diffeomorphisms, etc. There are a lot of difficulties in doing that. The first is that if I take the limit small l goes to infinity in all of this, it just fails dramatically. I mean, none of this is well defined because the line element blows up, for instance. So we are going to address this by changing our gauge. We're no longer going to use Pfefferman-Graham, but we're going to use something called Bondi gauge. And the other difficulty is that, contrary to ADS-CFT, the conformal boundary of asymptotically flat spacetimes is not time-like, but it is null. And There was a really nice conference this week about non-Lorentzian geometry. The null boundary is the prototypical example of what we call the Carrollian geometry. Carrollian is just another name for a null hypersurface, or any null manifold in general. And as I was saying also in the introduction, the thing that makes any attempt to flat holography hard is that, contrary to ADS-CFT, where you have a conserved stress tensor, in asymptotically flat spacetimes, the quantities that enter any putative holographic stress tensor, like the mass or the angular momentum aspects, they're not conserved. There is no way of rewriting Einstein's equation such that it becomes a conservation equation. However, we are going to derive this equation from the same line of reasoning, namely invariance under diffusion. So they are not a conservation equation, but they are consequences of a very fundamental fact, which is that any theory, any boundary theory that you write should be diffeomorphism invariant. Okay, so if there is no question about this plan,
You are going to consider a boundary of in radial infinity now.
no, null infinity. So I'm going to jump to this.
Yes, it's null infinity. Flat spaces conform to U2, group manifold U2. So
Flat space, so four-dimensional flat, sorry, I didn't get it, but
yeah, for four-dimensional flat spaces conform to the group manifold U2. So
you two like the
yeah, yeah, just as an old result.
Oh yeah, okay. In the
Try to see where the
okay, so maybe it's going to become clear in just a moment. So yeah, so just to start with, maybe just a picture. So if the Penrose diagram of asymptotically ADS spacetimes looks like a cylinder, for asymptotically flat spacetime it looks like this, and we here have two interesting loci, which is scri plus and scri minus. Both are null manifold, and they're three-dimensional, isomorphic to R plus S2. The R direction is the line that is represented here. Coordinates are usually called U, retarded time. Here it would be V, advanced time, and some angles, X, I, on the sphere. So yeah, this is going, I don't know if this answers your question, but this is going to be the manifold. U2, yeah. Is that U2? So, okay, so let's try to limit the steps taken here. Start with ansatz. The one that I'm going to use is called the Bondi gauge. It was derived some time ago, used to study gravitational waves in asymptotically flat spacetimes. And yeah, I'm just going to focus here near scruples, future non-infinity. You can do exactly the same reasoning for scri minus. So there's going to be a bunch of functions that appear. Not all of them are going to be important for us. So yeah, and I'm going to, similar to the boundary conditions of ADS-CFT, I'm going to specify what are my boundary conditions here. And it's that GRR is equal to 0, GRA equals 0, and something a little bit weird, which is that the determinant of this metric GAB is fixed. It's equal to R squared times the determinant of this metric, which is the metric of the units. Okay. And all of the objects here have some 1 over r expansions, where r is the distance to the boundary. So I have retarded time, sort of holographic coordinate r, and then some angles. And I'm going to expand everything in power 1 over r. And there's going to be some objects that are important. Yeah, so now this is 2. That's 6 times. So, okay, beta is not important for us here. V over r, it starts with minus r over 2 plus 2m over r. This big R is the radius, is the Ricci curvature of the 2 sphere. And just set it to a constant if you want. Then there is this mass m, mass aspect m that appears here. Why we call it a mass aspect is because if you have, let's say, a Schwarzschild black hole in your space-time, its mass would enter here.
I understood beta is a function of.
Yeah, beta is also going to have an expansion. So it starts with beta 0 plus beta 1 over r plus beta 2 over r squared. Typically, we take this guy to vanish, right? Then this guy is set to 0 by Einstein's equation. And this beta 2 is fixed in terms of some other geometrical quantities that I will introduce just in a moment. Then we have this GAB. So GAB is going to start with the sphere metric, plus R, CAB, etc., etc. This determinant condition that I wrote here actually tells you that all the tensors that appear here are traces. So if you take this determinant condition, expand it in powers of 1 over r, okay, at leading order you get just an identity, and then at next and next to leading order you get that CAB gamma AB is equal to 0, etc., etc. Okay, and finally, UA. So here I already solved Einstein's equation in order to express this line element in terms of quantities that are interesting for you. And you see here, so here we have M. Let me take some time here. So we have M, and we also have NA, that are 2 integration constants when you solve Einstein's equations. They are not constrained at this point. They will be when I will write down the remainder of Einstein's equations. And we also have this object, CAB, which is called the gravitational shear. And the reason is that it's measuring the distortion of space-time in both directions, let's say transverse and longitudinal, due to the passage of gravitational waves. So this CAB is also a completely free data, which encodes gravitational waves. And it's going to be the main, let's say, the main protagonist of why this construction in flat space is more difficult than in ADS, because this CAB is responsible for the non-conservation of the mass and angular momentum aspects. So to finish this part about asymptotically flat spacetimes, I'm just going to write down the 2 important equations that will be we will try to introduce in the following. And the first one is called the Bondi mass loss equation, because it's describing how the mass aspect is evolving, along the retarded time direction. So it starts with this term, which is a total derivative. Yeah, I didn't say that. N, the retarded time derivative of shear. And then it has a piece which is responsible for the loss of mass in the bulk because of this negative sign. And so this, which is non-zero if you are not. There is a similar evolution equation for the angular momentum aspect, but I'm not going to write here because it's long and it's not particularly informative. So, yeah, it's also not conserved due to the presence of this Bondi Muse tensor. Okay, so this is what I'm going to call the Flux-Balance laws, because that's their name. And this is what I'm going to try to reproduce. Let me say that these play a similar role to the conservation of the stress energy tensor in ADS holography, in the sense that you have some time evolution of a scalar and time evolution of a vector. But they're not directly, okay, they're not directly similar to this conservation equation. However, if you start with an asymptotically ADS spacetime in this case, you can write an asymptotically ADS spacetime in this case. You write down the conservation of the holographic stress tensor, and then you take the cosmological constant to 0, you land precisely on this. This is was proven by Adrian collaborators, and recently re-derived the paper Arius collaborators. So that's why we know that these two equations, they play a similar role to the conservation of the holographic stress tensor in ADS. Any questions?
So, I'm trying to just get in my head exactly what your metric looks like at the leading order of that infinity.
Okay, that's very good. So, at leading order, so okay, talking about leading order, it's a bit hard to see it with this metric because powers of R are a bit messed up, right? So in Pfefferman-Graham gauge, it's really easy to peel everything in powers of R. Here, it's a bit more complicated, but if you go to conformally compactified spacetime, then it's really clear. Conformally compactified spacetime, just you replace, for instance, R by 1 over rho, and you send rho to 0. And then you read off at each power of rho what is the metric. So you will find that ds squared conformally compactified starts with r to the rho to the 0 times the metric which is degenerate. So yeah, that's why I was talking about Carrollian.
But it's always degenerate on the null surface and that null sphere is infinity, so that's nothing strange.
No, that's perfectly compatible with the nature of non-infinity. Yeah, but it's making sometimes things a little bit more complicated from computational. Now, sorry, our boundary metric is degenerate. So we cannot.
Is it possible to just write down what that metric you've written over here is, just to feed in your leading conditions on it? It looks like it's just going to be some capital R times R over 2, probably du squared.
Yeah, that's right. That's right.
And you've just a constant du dr, and so you now have derivatives. You have dx minus a derivative of dB of c. Is that what it is?
Yeah. This piece comes from solving Einstein's equation. The important thing is that if you set, let's say, CAB to 0 and a lot of other things to 0, basically you take this equal to constant, let's say 2, mass aspect is set to 0. This reproduces the Minkowski metric, but written in advanced. So Minkowski is just going to be ds squared minus du squared minus 2 du dr plus r squared ni dx. So this is Minkowski, empty Minkowski space, and then we introduce some sublimiting.
Yes. Yeah. So it's equivalent to this, what your conditions are equivalent to that.
My boundary conditions?
Yes.
It's okay, so the boundary conditions, it's more, I mean, you do recover Minkowski at leading order, but it's, yeah. Okay, so now, okay, I've written down this Flux-Balance laws. So, okay, if you haven't understood anything so far, let's say, the goal now is to find some boundary variation in principle. By boundary, I mean something that gives prime plus, such that these flux balance laws are consequences of this variation in principle when you, let's say, require that the boundary action is invariant over diffeomorphisms, local Dye transformations, and so on. Of course, what we have in mind is that we would like to have a microscopic description for this boundary action. Let's say, take S boundaries, a bunch of scalar fields or a bunch of vector fields, some n equals 4 super is one not, but some null version of that. And when you take the variation of this boundary action, you compute a stress tensor. And this stress tensor is what encodes the mass, angular momentum, and its conservation would be these equations. We don't have any microscopic description of this theory because we don't have any idea what the dual pair of gravity, Einstein gravity with zero cosmological constant is. But what we can do is to say, okay, if I have such a microscopic candidate, then its variation has to be what I'm going to write. Because this is what allows me to recover Einstein's equation. So, okay, I'm not going to fill in this just yet. First, I'm going to I'm going to make a Carrollian interlude. Remember that Carrollian means null geometry. So we know that null infinity is a Carrollian manifold. It's actually more than that. It's a conformal Carrollian manifold because it's a boundary at infinite distance. So in the same way that the ADS conformal boundary the metric in the ADS conformal boundary was equivalent up to Weyl scalings, there is going to be a sense under which our boundary geometry is insensitive to Weyl scalings. So let me write it like this for the moment. This is the degenerate metric at strike plus. And what I'm going to do now is to actually switch to a first order or Filbine formulation, because it's going to prove to be easier to work with. And it's going to be easier to work with because we don't want to deal with degenerate metrics. So let me introduce object that I will call the clock form, which is measuring how time is evolving in the null direction. That is, you can think of it as being du. and then two space-like one forms, which represent the angular mode. So this is a co-frame. Its dual is going to be a frame with, again, three vectors. The first one, upsilon, is the vector aligned with the degenerate direction of this metric. So it's, roughly speaking, partial U. And then these two are chosen to complete the basis. There is also a volume form that you can build by just taking the wedge of these three guys. So this is the first order formulation is actually very powerful, because when you are given a set of a basis of vector fields or basis of one forms, you don't have to worry anymore about raising, lowering indices, if the metric is null or not. You're just working with this. So one point is that this choice of base is actually not unique. There are many symmetries that are acting on this. For instance, there is local rotation. Right, like this. So this you have to think of this as the null or Carrollian analog of local Lorentz transformations. One or two. There is also something called local Carroll boost. Which is acting on the clock form. And all these parameters are AB. So RAB is antisymmetric. And lambda A is a vector. It's a function of spacetime, boundary coordinates. And then you have also local Weil transformations that send forms to minus B times themselves. Vectors to B times themselves. So from this transformation, you can actually read what is the Weil weight of these objects. We say that the co-frame has the Weil weight -1, but the frame has Weil weight of 1. And okay, you can start to look at these transformation laws and think what are the objects that are invariant, covariant under these transformation laws, and you will see that theta A, theta B is invariant under local rotation and local boost, and under local Weil transformation, it transforms with a weight -2. And on the other hand, the field of observers that we call upsilon is invariant under local rotation, local boost, and transforms with weight +1. So yeah, this is how we are going to parameterize our background geometry. But this is not all. We also need to specify what is the connection that we build. And this is where things are starting to get interesting. Because if you take a connection and you ask that it be torsion-free and Weil metric compatible, in the sense that this is verified. Then you will realize that it's actually not unique. But first, let me tell you what is this alpha. So this alpha is a one form that we call the Weil connection, because remember that we are dealing not with a single metric, but a conformal class of metrics. So if I ask nabla theta is equal to 0, this is not invariant to the value scale. So we introduce this guy as a, let's say, an auxiliary field in order to compensate for this change of life rate. So we impose these two conditions, the distortion-free and volumetric compatible. This is actually not sufficient to fully constrain what is this nabla. Right, so there is no, this is something very well known in non-Lorentzian geometry, that there is no direct analog of the Levi-Civita connection. So, yeah, let me say it in words. So, nabla has ambiguities, things that are not fixed by these two requirements. And namely, so if I call omega A and C A, the components of this connection, then there is an ambiguity which is encoded in omega 0, A and B symmetric. And so if you remember, when I was writing the expansion 1 over R of an asymptotically flat spacetime, I had also an ambiguous tensor that was appearing.
You didn't write your metric in terms of your forms. So you told us what the volume form is. Oh, you're saying this is what you?
Yeah, this is my metric. Yes,
it is. Yes, where it is, and those are over just the two elements.
Exactly. That's why it's degenerate, and the degenerate direction is precisely this vector here. So yeah, so when I was writing the form of an asymptotically flat spacetime, I had this tensor CAB that was appearing that I called the Bondi shear. Pekar showed that Bondi shear is encoded in the boundary connection precisely in this ambiguity. There is just one subtlety here, is that my boundary conditions were such that CAB is traceless. This is not traceless, but you can extract its traceless part, and this is going to include gravitational degrees of freedom. Okay, so this was the very fast course in Carrollian geometry. Now let me go back to my variational principle. I write it on shell, in the sense that I don't know what is my macroscopic description here, but I don't care. I'm just going to go on shell for the equations of motion of matter fields. I'm only interested in how the theory reacts to a change of geometry. This is how you extract the stress tensor, because you couple your theory to background geometry, you vary with respect to the geometry, and you recover the Einstein-Weber stress tensor. Here it's going to be a bit more complicated, but still very manageable. So we start with the volume form. And then I have two possible variations. The first is with respect to the triad. I'm going to denote collectively as theta A. So A is from 0 to 2, small a is from 1 to 2. This is a one form, and the response is going to be a vector that I call TA. It's going to be the analog of the stress tensor. But it's not finished because we know that we have some ambiguous parts in the connection, some unconstrained parts. So we also have to vary with respect to that. And the response is what we usually call the hypermomentum. Maybe a small note here. So even though only this component of the connection is unconstrained and arbitrary, I'm going to vary with respect to all of the spin connection. This is a choice, right? I can decide that I work in metric anti-gravity, for instance, and I treat the field-line and the spin connection as two independent objects. So that's why I have these two tensors here for all values of AID. What I like to think of is that not only, actually, let me reformulate that. The reason why we have this omega AB, which is arbitrary, which is, sorry, the response to all of the spin connection is a consequence of Einstein's equations. We don't have this under control yet, but we are going to work on that to prescribe the form of omega AB, this guy, coming from Einstein's equation. But for the moment, we're just going to assume that this is true and derive Einstein's equation from that. So I don't have a whole lot of time, but I'm going to flash out what are the steps that we need to do starting from this variational principle in order to recover Einstein's equation. The first one is to ask that this S boundary is invariant under local symmetries. And these local symmetries are local rotation, local Carrollian boost, local Weyl transformations, and diffeomorphism invariance. Each of these requirements is going to give me some constraint or some evolution equation that are going to take the form T A B is equal to this. So this curly D here, it's a Weyl covariant derivative. So it's minus the weight of the objects times the Weyl connection. So this is the equation that you get by asking invariance under local rotations. You also have invariance under Carrollian boost. This Weyl constrains the trace of this T tensor. Finally, diffeomorphism invariance is going to give us some evolution equations. So it's a bit of a mouthful, but you really have to think of these equations as the flat space equivalent of the conservation of the stress energy tensor, holographic stress tensor in ADS. It doesn't look like a conservation equation. In fact, it's not, due to the presence of this term here, Riemann tensor times hypermomentum. And this is what is going to explain, let's say, this Flux-Balance laws. So, yeah, this is very simply, you evaluate this variation on a local rotation, boost, Weyl, or diffeo, and then you extract these equations from the variation. So, okay, we are nearly done. The thing that I want to do now is to take these equations and make a choice. So the choice that I'm going to make is to go to the BMS frame. And the BMS frame is just tau is du. This is how we choose our asymptotically flat metric to look like. Theta A is a one form. Theta A, this is a bad notation, sorry. theta I of x dxi. Yeah, so I had capital A in the next section, but capital A is already taken, so I'm going to denote the angles by I. Which denotes partial U, and EA is whatever you need to for this to be the inverse of that. So this is just a choice of gauge, right? And now I'm going to put this inside of these evolution equations, and I'm not going to write everything, of course, but in the end, what we have is to specify these objects. And we found that the choice that reproduces this BMS flux balance laws is that T00 is just 4 times the Bondi mass aspect. This is going to be twice the angular momentum aspect, plus 1/16. That's this combination. And okay, I'm not going to write the prescription for the angular momentum, for the hypermomentum, because it's going to be too long and it's not going to explain you what is the main message. The main message is that with this choice of momentum and hypermomentum, which you can think of as a prescription and a prediction for a holographic stress tensor, you can reproduce the BMS flux balance. So that's already a good point. The next thing that is also very encouraging in our approach is that if you look at this boundary variation, which is unevaluated, so I leave the delta as it is, you will find that there is inside here one term, which is delta omega 0 AB, omega 0 AB. And in our prescription, omega 0 AB is Bondi News tensor. This guy, I said it was the shear. So the term that we have is variation of the shear times the news. And we recognize this term as the Pekar-Streubel symplectic potential for asymptotically flat gravity. So this is, let's say, comforting us that we are on the right track. And I will say the final piece of evidence that this choice is the good one is that if you compute the boundary term associated with this variation, and this is going to give us the charge, then what we produce is I'm not going to write the expression, but it's T0A times psi A. So this psi 0 and psi A is a diffeomorphism. And when I compute the boundary term for this variational principle, I land on this. And this expression was found some years ago by Glenn Barnish and collaborator, and it corresponds to the BMS charge. Okay, so in summary, what we did is to propose a boundary variational principle for asymptotically flat spacetime that is formulated intrinsically to null infinity, and which we can use to derive the BMS flux balance laws. It also reproduces a lot of things that were derived in the literature concerning asymptotically flat spacetime, so the presymplectic potential and the other charges. And yeah, what we would like to do next with that is to maybe revisit the AES-CFT construction involving the holographic stress tensor, but now in Bondi gauge instead of Pfefferman-Graham, because if you're using the Bondi gauge, you can safely take the limits of vanishing cosmological constant. And this will allow us to give a physical meaning or a physical definition of radiation. The other thing that we will need to do is to provide a justification for why these hypermomenta omega AE are what they are, and we want to derive them for Einstein's equations themselves, not only check that they reproduce Einstein's equation. And finally, we want to take this to the next step. So this is, let's say, a prescription for what a boundary variational principle should look like, but are there any theories that reproduce this boundary variational principle? Namely, are there any microscopic Carrollian CFTs that when you take their variation, they couple not only to the geometry, to the background metric, but also to the boundary connection, because this is an absolute requirement if you want to reproduce BMS flux balances. So yeah, I guess I will end here, and thank you for your attention.
Any questions?
So you have the variation, but you only have it on shell.
On shell for the matter fields, yes.
I'm not sure what it means to say on the matter fields. It means there are no matter fields to be seen here, so I don't know what that means.
Yeah, precisely. We wrote this variational principle by saying, imagine that I have a Carrollian CFT for some matter fields that are, for the moment, unspecified. Then, if I couple it to the geometry, take the variation, this is what I should obtain after I impose the equations of motion for the matter fields. Or I can also
there's no way of integrating these back to get an action. Which was the variation of those, is what I'm getting.
No.
You can't take another variation because you're sitting on shell. That's what you mean by on shell, probably.
Yes.
So you only have the first variation.
Yeah, okay. Another way to think about it is that imagine that I had a holographic renormalization scheme for gravity in flat spacetimes. Then what I should obtain as the renormalized on-shell variation is this, at leading off. Without making reference to any matter fields or any CFT tool. But you're right that this is an on-shell definition. Sorry, this is a variational definition of S boundary. I cannot remove the delta in this equation.
And you also don't know that there is an S boundary for which this is the variation.
Oh no, we don't know that. We just
postulate
that it exists.
Yes, but yeah, you have no way of checking that there exists an S boundary.
Well, that's what we hope.
This is a one form on the space of field, on certain space of fields, but you have no way of checking that it's a closed one.
It's not closed. It's not.
So if it's not closed, then it's not the variation of any.
It's not. Well, we know that it's not
S boundary.
Sorry.
If you know that it's not closed, then it's not the variation of any S boundary.
Okay, so this I wouldn't say that I'm an expert in this, but if you are using covariant phase space methods to derive the symplectic potential for GR, that space, we know that there is a non-exact piece. The Ashtekar-Strognov symplectic potential is not the result of the variation of some action. So whenever you are writing down a variational principle, there is always an integrable part and a non-integrable part. The integrable part is usually the charge, and the non-integrable part is what gives rise to the non-conservation. And this, we know that it's not the variation of anything. Maybe Adrien, if you have a...
Yes, actually from the first place, when you write this kind of equation, you define the TA as the vector obtained by the variation of the S boundary with respect to theta A. So it's tautologically closed, because the TA is the variation of the putative action with respect to theta A, and so it is for the capital omega with respect to the small omega. So we are assuming that there exists an action of the boundary, we don't know anything about the microscopic description, but this action should exist for the holographic principle to work.
I know, but from what I can understand, there's no way of checking that that statement is true. I mean, if I give you a set of differential equations, which are some set of equations of motion of something, I can check if they came from an action by taking the next variation of those equations. And it's equivalent to check, and it says if they're symmetric, then the anti-symmetric part of it is zero, and it came from the variation. It's like the gradient of a potential. But here,
exactly. Okay, I understand better your question now. So the thing is that on the boundary, if you have access to a microscopic instance of your boundary theory, you will have some matter fields that Simon has put on shell. So this equation of motion, basically, you can ignore them because they will not give you the gravitational flux balance law. Because these ones are rather related to the variation with respect to the geometry. So you have to set the boundary matter fields on shell. But you are right, if you give me a differential equation for these matter fields that we assume here on shell, there is no guarantee that they come from an action. But one of the zero step of the holographic correspondence in this picture is to assume that such an action exists. And then what we show is that we can derive the boundary, okay, the asymptotic equation from this. But that's an axiom that we have to take in holography in general. It's also taken in ADS-CFT. So, I mean, it's as iconoclastic as in ADS-CFT.
And we can thank the speaker again.